All right, welcome to lesson 8 of unit 2. This is our second last lesson, so we're busy wrapping things up. So we're looking at composite functions. So whereas our previous 2 lessons have been about combining functions, that's looking at like adding, subtracting, multiplying, dividing, using those different operations with functions. Composite functions means literally taking one function and putting it inside another one. So we word it as, and we see it right here, if I write g inside of f, I'm going to word it as f of g at x, or f of g of x. So that's kind of the language you're going to be hearing. So when we do this, what does that really mean? Well, it means that we're going to solve that inside function first and then apply it to f. So going for our first one, we say when g is, what is the output when x is -1, looking at the function of g? So the output is 2. So I could say that I'm instead looking for f of 2, because that is what this piece is equal to, based on looking here. Once I've got that, then I can look at my table of values for my function f and say when x is 2, because it's in place of where x should be in our normal notation. So 2, well, the output is 0. And so that would be my final answer. That's all there is to it. It's just a matter of like putting one output in as the input of a new function. So we go to the next one, f of 1. So that would simplify to f of -1, because if I just looked at f of 1, I see that the output is -1. When I look at f of -1, I see the output is 3, so that would be my final answer. Lastly, if we reverse it, we can do g of f of x, wherein f is 2, so, or when x is 2, so 2, the output is 0. So really we're doing g of 0, and based on that, my output should be 1, according to my g function. So that's what this is all about. It's about kind of inputs to outputs to inputs to outputs. So we've got a few different ones to practice. Now, this image apparently bumped down for some reason. So we'll call these graphs f of x, we'll say is this one, and g of x is the other one. So I'm just going to transpose those questions. G of f of -2 and g of f of 3. So looking at the graph again, we can look at these values and say, okay, well, f is -2, or f at x equals -2 rather, is +8. I then look at my x value at +8 and find my g output, and that is 3. Conversely, if I'm looking at f when x equals 3, it's -2, so I'm going to go to -2. Well, g does not exist at x equals -2, so we would say that does not exist. Okay, it's outside of its domain. Example 3. So we can do this algebraically as well. So you can set it up by just plugging it into one and then plugging it into the other, or you can actually create an equation where it's all in one. So that's what I'm going to do. So f, I'll just do it off to the side here, f of g of x would be, if we put this in place of x in my f function, so absolute value of 1 over x squared plus 1 minus 1 would be my function that I can use here. Given this, I can plug in 2 for x and be able to solve this. So absolute value of 1 over 2 squared plus 1 minus 1. So that would be 4, 5, so 1/5 minus 1 is the absolute value of negative 4/5. You could also do it stepwise, plug it in, solve for g of 2, which would have given you 1/5, and then solve for f of 1/5, and go from there. And both would result in the same answer. Okay, if I did g, and I'm going to use a different notation, so g of f of x, then I would be putting in my absolute value into my other equation. So it would be 1 over absolute value of x minus 1 squared plus 1. So again, using that equation, using that algebra, I'm going to go 1 over absolute value of 2 minus 1 squared plus 1. 2 minus 1 is 1, squared is 1, plus 1 is 2, so this should be 1/2. And again, you could do it this way, where we break it into solving for f first, and then plugging that in and solving for g. And you should still get the same result. Feel free to pause the video and give it a shot now if you think you may prefer this method. Okay, so if f of x is 2x plus 3, find the inverse and simplify both composite functions. So what does that look like? Well, if f of x equals 2x plus 3, then we need to switch our quote-unquote y and x values. So I'd go x equals 2y plus 3, and then isolate y again. So that would end up being y equals x minus 3 divided by 2. And so that would be my inverse. Remember that notation of to the power of negative 1. Okay, so those are my inverse functions. Assuming that I'm calling the inverse function g of x, then we're going to work with these. So f of g of x would be 2x minus 3 over 2 plus 3. If I simplify, 2's go away. That leaves me with just x. If I do the opposite, x plus 3 minus 3 divided by 2. Oh, 3's go away, 2's go away, and it leaves us with x again. So in order for something to truly be an inverse, to know I've done this correctly, if I do either version of the composite of the original function and its inverse, they should always result in just equaling x. They should always kind of cancel everything else out. Okay, so that's what this statement is saying, is that when you're given x values for both compositions, both orders, then they must be inverses of each other. So what this next example is doing is basically getting to what I did in example 3. So the idea of being able to put one inside the other and being able to state its domain based on kind of what the principles that we would know, any sort of restrictions on non-permissible values, etc. So we're looking at f of x and g of x. We're going to be putting g inside of f to start, so putting this in place of x. We're going to do it in place of every x. So we should see the function g actually appear twice in here. I'm going to color code it just to kind of make that really apparent. So instead of x squared, I am going to write 3x minus 5 squared plus 3 times 3x minus 5. So again, you're seeing that blue in lieu of where the x's were. Okay, we can then simplify the function because right now this looks pretty complicated. It'll get more complicated before it gets simpler, but if we square this, we'll end up with 9x squared minus 30x plus 25 plus 9x minus 15. I think that's 9x squared minus 21x plus 10. So that's great. It leaves us with a little bit of a picture of what is going on here. And from here, we can actually state its domain. So this is a quadratic equation. And so we would expect the domain to be negative infinity to positive infinity. Okay, g of f of x. So again, I'll color code it. So it's 3. In lieu of x, we're going to write x squared plus 3x. What's the rest? Minus. Okay, so again, we can simplify this. 3x squared plus 9x minus 5. Again, only distribute into the brackets. And so again, we're dealing with a quadratic. And so our domain would be negative infinity to positive infinity. Our third function is a little weird. So we're going to try and write it with one within the other. So we'd start with x squared plus 3x. But that would have to be squared and then inserting another f of x within this function again. So it gets a little tricky. That's why I like to color code it, at least when I'm doing these videos, so that you can kind of track where it's all coming from. So again, the orange is the interior one, and the black is the exterior function for this one. Again, I would want to try and combine like terms as much as possible. So I'm going to go x, so I'd multiply this out. X cubed plus 9x plus 3x squared. Oops, that's 9x squared plus 9x. So I can simplify this to be x to the 4 plus 6x cubed plus 12x squared plus 9x. Now this is a much more intense kind of equation. This is what we're going to be working with when we start working with polynomials. We're not going to look at range right now, so we don't need to worry about that piece. And there are no non-permissible values, so I would still expect with any polynomial that my domain would be negative infinity to positive infinity. And you can always check with Desmos while you're doing these questions to be confident in your answer. But as a rule, if there's no non-permissible values, and there's no obvious restrictions such as square rooting of negative numbers, or not allowing 0 to be in the denominator, then you should be good to go. Perfect. I was pretty sure that was our last example. So it's a quick little lesson. You've got lots of practice questions now combining back into lessons 6 and 7 as well. So give these worksheets a shot for sure. And then you've got one more lesson, and then you're good to go for Unit 2. And that's pretty awesome stuff. Keep up the good work and make sure you're always asking questions.